But what if I told you we could actually paint a picture of it? A high-resolution snapshot of every single gravitational...
Well, that's exactly what we're going to do. And here it is. This is it. This is the gravitational landscape. It looks kind of wild, doesn't it? It's complex. It's beautiful. Maybe a little chaotic, but trust me, every peak in every valley in this image tells a fascinating story about cosmic forces at play.
This comprehensive inquiry maps the intricate gravitational landscape surrounding Earth, quantifying how celestial forces exert measurable stress on our planet. We will specifically analyze the complex tidal and potential fields calculated for the 6-day period of early January 2026.
This analysis maps the dynamic gravitational forces anticipated in January 2026, using the 1917 celestial alignment as a historical baseline. We will use this forecast to identify and focus on high-stress zones across the globe.
The 1917 Saturn-Neptune alignment provides a critical historical precedent, coinciding with a sudden burst of global seismic activity. During this conjunction, the Earth experienced multiple major earthquakes across continents, including 2 powerful events exceeding magnitude 8.0.
The Moon, not the distant Sun, is the primary driver of tides because its proximity creates a powerful differential gravitational force. This force deforms the oceans into bulges, resulting in simultaneous high tides on opposite sides of the Earth. The Earth is constantly subject to a dynamic vector field, dominated by the primary tidal influence of the Moon and the secondary gravitational pull of Jupiter's mass. The alignment or opposition of these giant forces dictates the intensity and distribution of global gravitational stress. Focused on the precise moment the landscape emerged, this gravitational model maps intense zones of elevated stress concentrated across the Pacific and Eurasian tectonic plates. This data reveals the critical pressure points along the major fault boundaries during the analysis period. Within just 24 hours, the primary stress field has undergone a massive eastward shift across the Pacific Basin. This rapid migration is now concentrating potential energy directly along the western edge of the Americas. The gravitational potential is concentrating dramatically, revealing a critical band of heightened stress now extending directly across the entire Pacific Ring of Fire. This intensity confirms the increasing concentration of forces witnessed on January 7, 2026. The modeled stress field for this event precisely aligns with the major subduction zones across the Pacific Rim. Activity is concentrated in the northern and western regions, stretching dramatically from Kamchatka down to the Aleutian Trench. Our modeling indicates that on January 9, 2026, the gravitational potential reaches its peak modeled intensity, applying maximum stress across the North American and Pacific tectonic plates. On January 10, 2026, the tight celestial alignment ends, causing the intense global gravitational stress pattern to disperse and officially concluding the primary event window. Gravitational stress models overlaid on major U.S. fault systems reveal critical zones where external tidal forces amplify existing tectonic strain. This interaction pinpoints high-risk areas across the West Coast and the New Madrid seismic zone in the Midwest. Acapulco lies directly on the volatile subduction boundary where complex seismic stress is concentrated. On January 8, 2026, this critical zone experiences a powerful gravitational convergence, aligning forces from the Moon, Sun, and Jupiter. The historic 1917 Saturn-Neptune conjunction created extended stress across the southern Pacific, whereas the analytical 2026 model predicts a focused, multi-day gravitational peak targeting the northern hemisphere and North America via a Jupiter-Moon vector summation. We model the intricate gravitational environment of the solar system, mapping celestial tides to gain a unique perspective. This allows us to explore how these external forces might interact with Earth's internal dynamics and treating the hidden landscape beneath the surface as an unwritten scroll that holds the key to deciphering Earth's deep tectonic history.
The glow across the globe traces tectonic boundaries, where centuries of geological stress accumulate and are then suddenly released. The mapped locations represent 4 of the most catastrophic seismic events in recorded history.
Megaquakes are governed by the asperity model, where immense tectonic stress builds up in locked zones along the fault interface. The catastrophic main shock initiates at this highly stressed point, releasing enormous stored energy across the surrounding rupture plane.
Earth exists within a dynamic gravitational orchestra, where the combined shifting forces of the Sun, Moon, and all major planets impose an unceasing, rhythmic tidal stress on our world. This complex web of gravity influences everything from our orbit to planetary stability.
Tidal forces from the Sun and Moon cause the solid Earth itself to bulge by up to 50 centimeters daily, creating a continuous body tide. This physical deformation applies cyclical stress to deep fault lines, potentially influencing the triggering of seismic events. Examining the last 500 years suggests a link between major geological restructuring and the rare Saturn-Neptune conjunction, an alignment that recurs approximately every 36 years. This correlation is dramatically highlighted in the early 1950s, where 2 massive M8.6+ earthquakes immediately preceded and occurred during the 1952-53 conjunction window. On January 5, 2026, a unique planetary configuration aligns the Moon and Jupiter, resulting in a dramatic, amplified gravitational focus. This highly concentrated tension is targeted precisely at the mid-Pacific Ocean.
On January 6, 2026, the tightening alignment of the Moon and Jupiter shifts the net gravitational vector, creating maximum shear stress. This focused energy is concentrated directly over the critical subduction zones of the Western Pacific.
On January 7, 2026, the specific opposition of Jupiter and the Sun creates a maximum gravitational tug-of-war effect. This planetary alignment maximizes differential stress, concentrating the peak gravitational tide forces along the North and South American coasts. On January 8, 2026, the combined gravitational vector of Jupiter and the Moon reaches its theoretical maximum, focusing critical crustal stress directly onto the South American continent. On January 9, 2026, the near alignment of the Moon and Jupiter generates a sharply focused gravitational stress centered over South America. This peak pole is already beginning to weaken as the Moon moves past its direct alignment, causing the net force vector to shift orientation. The period of heightened gravitational stress from the celestial alignment has now concluded. As the planets shift, Earth's gravitational landscape returns to its standard background state, eliminating the window of elevated theoretical tectonic risk. Gravitational stress is a single, comprehensive global tension field that interacts continuously with the planet's specific underlying geology. Viewing the tension from these 3 perspectives, Pacific, Americas, and Polar, emphasizes the comprehensive, non-localized nature of these planetary forces. We have mapped critical North American stress points, showing where existing zones of high tectonic strain, such as the Cascadia and New Madrid regions, intersect with potential external gravitational pressures. This analysis highlights specific areas for further investigation into stress amplification, not serving as an earthquake prediction. Analyzing a future moment near the 2017 Tehuantepec M8.2 epicenter, the Moon and Jupiter alignment creates local gravitational vectors at near maximum intensity. This synchronization demonstrates how broad planetary forces translate into specific localized stress fields on Earth's crust. Our integrated model synthesizes terrestrial stress accumulation with celestial mechanics, such as planetary alignments and gravitational tides. This allows us to identify specific windows where critically stressed faults enter periods of heightened tectonic sensitivity. The historian's duty is to relentlessly track and interpret the complex, continuous rhythm of the world's unfolding story, ensuring that what we convey to posterity is done with a study on the gravitational landscape, an analysis of the planetary stress vectors that influence activity across Earth's major tectonic plates. We will specifically examine these geodynamic forces acting upon the planet during the period of January 11th through 31st, 2026. Earth's familiar tides are primarily driven by the moon and sun, but the overall gravitational stress field is constantly being modulated by the immense, long-period influence of gas giants like Jupiter. We quantify this complex differential to accurately measure the total forces acting on the planet. We model the cumulative gravitational pull of every major celestial body, highlighting how the dominant influence of the Moon and Jupiter results in an extra stress landscape. This visualization pinpoints areas of peak gravitational tension across Earth's lithosphere at any given moment. The 1917 M8.5 Kermadec earthquake serves as a critical historical benchmark for understanding gravitational stress. This event confirms that powerful planetary alignments, specifically the Jupiter-Moon opposition, created a focused stress vector capable of triggering major seismic activity in the South Pacific. On January 11, 2026, the Pacific Basin entered a period of heightened tectonic activity, marked by widespread stress. Critical pressure points are focused on the Kamchatka subduction zone and the Wharton Basin. A near-maximum Jupiter-Moon alignment is rapidly intensifying the global stress field. This focus of gravitational tension places critical risk on high-activity seismic zones, particularly along the coast of Chile and the Aleutian Arc in Alaska. January 28, 2026 marks the predicted moment of peak gravitational tension across the globe. This maximum stress, driven by a specific planetary alignment, creates a powerful trans-Pacific tension axis focused intensely on the Eastern Pacific. Our analysis models a daily gravitational stress peak hitting the Middle America Trench at 7:55 a.m. every morning. This recurring extra stress is the critical external trigger that, combined with dangerous local geological resonance, has the potential to amplify seismic effects catastrophically. High gravitational tension is concentrated along known fault lines of the West Coast, but this analysis also pinpoints a severe stress hotspot converging on the New Madrid seismic zone in the American heartland. While both the 2026 forecast and the 1917 event share similar vector alignments on the Pacific Plate, the geographical stress location is drastically shifted. The 2026 peak stress is concentrated heavily along the Eastern Pacific and the Americas, contrasting sharply with the Southwest Pacific focus of the 1917 benchmark. Our investigation identified a quantifiable gravitational force leading to a major stress landscape in January 2026, focusing heavily on the Pacific and American plates. This high-tension period mirrors historical patterns and pinpoints specific, vulnerable seismic regions for
Ever stop to think about the invisible forces that are pulling on our planet, like right this second? We're talking about gravity, of course, but it's not just our gravity. It's this massive cosmic dance, choreographed by the sun, the moon, and all the other planets, and they are all pulling on our world every single moment of every day.
So let's just jump right in. We all know the planets are out there, doing their thing, exerting their pull. But have you ever wondered what that pull actually looks like? Can we see it? Well, that's exactly what we're going to do. We're taking some incredibly complex astronomical data and turning it into a visual story of gravity's very real and very powerful impact on us.
Okay, so to even begin to see these forces, the first thing we need is a map. And not just any map, we need a really, really precise map of the entire solar system.
Gravitational tides create opposite stress patterns globally. As one side experiences maximum tidal stress, visible along the Western Americas, the opposing hemisphere simultaneously registers the corresponding minimum tidal effect. Tidal effects are fundamentally twofold. The land flexes during the body tide, which then combines with the flowing ocean tide to create the total gravitational landscape we measure. The dynamic pull of ocean tides shifts dramatically, with vectors illustrating how both intensity and direction change based on the specific geography of the US East and West coasts.
It's not a map of countries or oceans. It's a map of the invisible forces that shape everything. And it's all frozen at one single moment in time, January 4th, 2026.
So, let me ask you a question. Is the pull of gravity the same everywhere on Earth? You'd probably think, yeah, of course, it's just a constant downward pull. But what if I told you that's not even close to the whole story? What if the very ground beneath your feet is actually rising and falling, stretching and squeezing in this silent cosmic rhythm?
Yeah, the real answer is way more complex and honestly a lot more beautiful than you might think. So let's dive into this hidden landscape of forces. We're going to peel back the layers on gravity and show you a world that is always in motion, shaped by a constant dance between planets and stars.
To really get this, you can't think of gravity as just one simple force. You've got to see it more like an intricate tapestry, one that's woven from two completely different kinds of threads. One that's totally permanent, and another that's, well, changing all the time.
And this right here is the perfect metaphor to help us understand it all, the warp and the weft. Just think of the warp as the fixed, underlying structure of the tapestry. That's Earth's own gravity. The weft, on the other hand, is the colorful, dynamic pattern that gets woven across it by the poles of the sun, the moon, and all the planets.
All right, so let's start with the foundation of this whole tapestry, those permanent threads, the fundamental structure of gravity on our planet. This is the warp. You know, if Earth were just a perfect smooth sphere with the same stuff all the way through, gravity would be the same everywhere, but it's not. As this map shows, our planet is gravitationally lumpy. You've got dense mountain ranges like the Himalayas creating these strong poles, while deep ocean trenches create weaker ones. This is Earth's own gravity, the static, unchanging map that forms the background of our gravitational world.
Okay, now let's move on to the weft, those dynamic threads that are woven across that foundation. These are the patterns that are constantly changing, created by the gravitational pulls from the sun, the moon, and the planets. They change the picture from moment to moment.
Now here's the key thing to wrap your head around. Tidal force isn't just a simple pull. It's what we call a differential stretch. The moon, for instance, pulls hardest on the side of Earth facing it, and it pulls the weakest on the far side. It's this difference in the pull that actually stretches our planet out, creating those familiar tidal bulges. Our entire world is constantly being stretched.
Have you ever stopped to wonder what gravity actually looks like? I mean, we feel it every second of every day, right? It's this invisible force that keeps us grounded. But what if I told you we could actually paint a picture of it? A high-resolution snapshot of every single gravitational force pulling on our planet at one specific moment in time. Well, that's exactly what we're going to do.
And here it is. This is it. This is the gravitational landscape of our entire planet on January 4th, 2026. It looks kind of wild, doesn't it? It's complex, it's beautiful, maybe a little chaotic. But trust me, every single swirl of red and blue, every peak and every valley in this image tells a fascinating story about cosmic forces at play. So, the big question is, how do we get a picture like this?
To get there, we have to understand a key idea first. The gravity we feel isn't just one simple thing. Nope, it's actually a combination of different forces all mixed together. So let's break down the ingredients that go into making this incredible, intricate portrait. You know, the best way to think about it is like a giant, cosmic tapestry. It's woven from two totally different kinds of threads. First, you've got what are called the warp threads. These are the strong, permanent threads that form the foundation of the whole thing. That's Earth's own gravity. Then you have the weft. These are the dynamic, constantly changing threads that get woven across the foundation. And those are the pulls from the sun, the moon, and all the planets.
Okay, so let's start with that foundation, the warp. This is the gravity that comes from our planet itself. It's the baseline, the canvas that everything else gets painted on. Now, what's so cool about this is that it shows Earth's gravity isn't perfectly smooth. You might think it is, but it's not even close. If our planet were a perfect, featureless sphere, it would be. But we've got massive mountain ranges, super dense rock deep underground, and incredibly deep ocean trenches. All of that uneven mass makes our planet's own gravitational field wonderfully, well, lumpy. This is the permanent structure of our tapestry. All right, so we've got our foundation threads. Now let's look at the other part of the story, the weft. These are the dynamic, ever-shifting pulls from space that are constantly weaving new patterns across the warp. So this chart shows us who the main actors are in this cosmic drama. When it comes to the forces that actually stretch and warp our planet, the moon is by far number one. It's just so close to us. The sun, even though it's gigantic, comes in a distant second with about 46% of the moon's effect. And all the other planets, like mighty Jupiter and Venus, their combined influence is less than 2%. It's tiny, but it's still part of the weave. Now, this next point is absolutely crucial. We're not just talking about a simple gravitational pull here. We're talking about tidal forces, and that's a whole different ballgame. A tidal force isn't about pulling the entire planet. It's about the difference in the pull from one side of the planet to the other. It's not a pull, it's a stretch. Look at this, it shows exactly what I mean. On the left, you see the total gravitational pull just kind of tugs the whole Earth along in its orbit. But look at the right. That's the tidal force. The pull is stronger on the side of Earth facing the moon, and it's weaker on the far side. That difference, that differential, is what stretches the planet out, creating bulges on opposite sides. That's the engine that drives our tides. And here's what those stretching forces look like, all mapped out for our target date. This is the weft, all by itself. The red zones are where the planet is being stretched outward the most, creating what you could call gravitational high tides. And the blue zones, that's where it's being compressed. This is the fleeting, transient pattern that the cosmos weaves every day. Okay, you with me? We've got the warp, that's Earth's lumpy gravity, and we have the weft, that's the cosmic tidal stretch. Now it's time to bring them together and weave the final tapestry. So let's step up to the loom and see how this works. First, we lay down that permanent static foundation of Earth's own gravity. Remember all those lumps and bumps from its mountains and trenches? That's this. And then, right over the top of that foundation, we weave the dynamic, fleeting pattern of all those celestial tidal forces, frozen in time for January 4th, 2026. And here we go. This is the result, the final, complete tapestry. This image is the true, total gravitational pull felt right at the surface. It's the sum of our planet's permanent lumpy nature, plus the specific cosmic alignment of that one day. It's a pattern that is truly unique and will never exist in exactly this way again. And what's really cool is this total force doesn't just pull on the oceans. It acts on the whole planet, but in layers. As you can see here, it actually flexes the solid crust of the Earth itself. That's the terrain tide. Of course, it moves the oceans a lot more dramatically. And the total effect we see is the combination of all of it. So that's the view from space, the grand cosmic picture. But what does this all look like when you zoom in? What does it mean for places we actually recognize? These three views give us a full 360-degree look at the planet at the very same instant. You can clearly see how the patterns are global, but they're also incredibly different depending on where you look. The gravitational landscape over the Americas looks totally different from the one over Asia and Europe. Okay, now this is where it gets really mind-blowing. Let's zoom into a continental scale right over North America. You can literally see the gravitational signature of the Rocky Mountains. That big red area of higher gravity is because of their immense mass. But at the same time, you can see this broader gradient sweeping across the country from east to west. That's the cosmic tidal pull layered right on top. It's local geology and cosmic forces woven together in real time. And check this out, if we filter out Earth's own gravity and look only at the tidal forces, just the weft, we can see exactly why this matters. Just look at the difference between the east and west coasts. On this particular day, the alignment of the sun and moon creates a totally different tidal pull on the Atlantic versus the Pacific. This is the direct cause of our familiar ocean tides. And just to really appreciate the scale of this, let's flip the planet over to the other side. The gravitational signature over Asia is completely dominated by that massive red anomaly. Any guesses? Yeah, that's the Himalayan plateau. It has so much mass that it creates this huge gravitational feature. This really drives home how the final picture is a true mix of the permanent Earth and the passing sky. So, we've deconstructed this beautiful, complicated image, but it's so important to remember what it really is. It's just a single snapshot, a single frame from a much, much longer movie. This quote really just nails it, doesn't it? This whole portrait is a pattern woven from the permanent threads of our planet's mass and the transient threads of celestial alignments.
It's the perfect reminder that this beautiful image is never static. An hour from now, heck, a second from now, the cosmic threads will have shifted and the tapestry will have already changed. Which really just leaves us with a final thought to chew on. We've captured the portrait for one day, but the planets and the moon are in constant motion, in an endless cosmic dance. And as they move, they are forever weaving a new and unique pattern across our world. So the real question is, what will the tapestry of gravity look like tomorrow? What if I told you that we can actually create a portrait of our planet's invisible forces? And not just from the past, but for a specific day in the future. Well, that's exactly what we're going to do today. We are going to deconstruct a scientific map of Earth's gravity for one single precise moment, January 4th, 2026. And here it is. Now, I know this looks like the end, but we're actually starting here. Just take a look at this. This beautiful, complex, swirling pattern of reds and blues. And you gotta know, this is not some artist's impression. Nope. This is a real, high-fidelity, data-driven map of all the gravitational forces pulling on our planet, specifically on January 4th, 2026. So, the big question is, what is this thing actually showing us? What are these invisible forces that are weaving this incredible, intricate pattern? Well, that's our mission today. We're going to peel back the layers of the single image and figure out the cosmic dance that creates it.
All right, to even begin to understand that image, we've got to kind of reset our basic understanding of gravity. Because, let me tell you, it is not what you think it is.
You know, we usually picture Earth's gravity as this simple, uniform force, right? Kind of like the old story of an apple falling from a tree. But the reality, well, you can see it on the right. It's just so much more complex. It's this wild, dynamic landscape of peaks and valleys, always shifting and changing. Our planet isn't just some solid blue marble. It's a world swimming in these invisible gravitational currents.
And here's the absolute key to understanding all of this. This landscape isn't shaped by just raw gravity. No, it's shaped by something called tidal forces. And what are those? It's all about the difference in gravitational pull from one side of the Earth to the other. I want you to remember this phrase. It's not the pull, it's the stretch.
Okay, this diagram here shows it perfectly. So you've got a celestial body, let's say the moon. It's pulling harder on the side of Earth that's facing it, right? And it's pulling weaker on the far side. Well, that difference in force literally stretches our planet out, creating these two bulges on opposite sides. And that stretching action, that's the real artist painting the portrait we're trying to understand.
All right, so before we bring in the big players like the sun and moon, we need to understand the canvas they're painting on, which is, of course, the Earth itself.
So I found a great way to think about this is to imagine we're weaving a giant tapestry. You have the warp threads, right? Those are the static, underlying threads that form the foundation. In our gravity picture, that's the Earth's own uneven mass. Then you have the weft threads, which are woven through the warp. Those are the dynamic pulls from the sun, the moon, and the planets, constantly creating new patterns across that foundation. So let's look at those warp threads first, Earth's own gravity. If our planet were a perfectly smooth, uniform sphere, this map would just be one solid color. But obviously it's not. You can actually see how gravity is stronger over dense mountain ranges, like the Himalayas, and it's weaker over deep ocean trenches. This is our world's permanent, kind of lumpy gravitational canvas. Okay, so the canvas is laid out. Now it's time to bring in the main weavers, the sun and the moon, to add their dynamic threads to the mix.
And here's architect number one, the moon. Now, it might be small, but it is incredibly close to us. And that proximity is everything. Its tidal force creates two really distinct high-stress zones on Earth, one right underneath it and one on the exact opposite side. Make no mistake, the moon is the undisputed king of the tide. Then, of course, we have architect number two, the sun. It is unimaginably massive, way bigger than the moon, but it's also incredibly far away. And that huge distance really cuts down its tidal effect. It makes the sun a powerful, but let's call it a junior partner to the moon. It creates a similar two-bulge pattern, just not nearly as intense.
This chart really puts it all into perspective, doesn't it? If we say the moon's tidal influence is 100%, the sun only comes in at about 46%. And what about the other planets, the big ones like Jupiter and our neighbor Venus? They barely even make a dent, less than 2%. It just goes to show you, when it comes to tidal forces, proximity is absolutely key.
So that brings us back to our specific date. Why January 4th, 2026? Well, it's because on that particular day, the sun, the earth, and the moon are all going to be nearly lined up. There's a cool word for this. It's called syzygy. And what this means is that their tidal forces are going to combine, they're going to work together, creating these extra powerful gravitational highs and lows across the planet.
But wait, we're not quite done. The sun and moon aren't the only weavers in this tapestry. To get that final, super detailed portrait for January 4th, 2026, we need to add the final touches, the subtle influence of all our planetary neighbors. Now, you have to look closely here. The combined pulls from Venus, Jupiter, Mars, all the other planets, they add that final, delicate layer of complexity. They're all tugging from different angles, and they subtly distort the main pattern that the sun and moon created. They're what add all those intricate, asymmetrical details to our final image for January 4th, 2026.
So, okay, we've built this beautiful, kind of abstract map of forces. But this is where it gets truly wild. This invisible ocean of gravity isn't just some drawing. It has a very real, and honestly, a pretty surprising effect right here on the ground we're standing on.
Now, we all know that these forces are what cause the ocean tides, right? The water sloshing back and forth. But that's only half the story. 55 centimeters. That's about 22 inches. What on earth could that number possibly refer to? Get this, it moves the very ground beneath your feet. The solid rock of the continents is being stretched and compressed by these exact same tidal forces. This causes the ground itself to rise and fall by up to half a meter every single day. The whole planet is basically breathing in and out in response to this cosmic rhythm. It's incredible.
And that brings us to our final and maybe most important point. This incredible, living portrait that we've so carefully built for January 4th, 2026, it's just a single frame in a movie that never, ever ends. See, the map we've been picking apart is totally unique to that one specific day. As you can see here, as the moon keeps orbiting and the planets keep moving on their paths, this whole pattern of gravitational stress is in constant motion. It's flowing and changing, not just day by day, but hour by hour.
And really, that's the ultimate takeaway here. Our world isn't some isolated object just floating in space. Every single moment of every day, it's being shaped and defined by its exact position in this huge, interconnected web of forces. It's part of an invisible landscape that has been sculpting our world since the very beginning. It really makes you wonder, doesn't it? If this incredibly complex and powerful system is operating all around us, completely unseen, what other amazing, fundamental forces are out there, weaving the even grander tapestry of our universe, just waiting for us to figure out how to map them?
Have you ever really thought about what makes the ground beneath us move? You know, back in 1985, a massive earthquake just devastated Mexico City, and in the aftermath, people were looking everywhere for answers. Some even looked up to the planets. But the real story, it turns out, is written much, much closer to home, right here in the crust of our own planet. So today, we're going to uncover the real forces that shape seismic risk, not just for Mexico, but for the whole world, from cosmic myths all the way down to the incredible stress building up on a fault line. All right, here's how we're going to break it all down. First, we'll bust some cosmic myths before we dive into the hard science of why our planet is always in motion. Then we'll look at how scientists can actually measure the strain building up in the crust and what the anatomy of a fault rupture really looks like. After that, we'll bring it all together with that crucial case study, the seismic threat in Mexico. And finally, we'll see what all this means for mapping out the real risks.
So, first things first, there's this ancient, deep-seated question we've always asked. Are we really at the mercy of events happening way out there in space? I mean, it's a huge question, isn't it? And you hear it all the time, especially when there's some kind of planetary alignment in the news. Can the gravitational pull from other planets actually set off the next big one? You know, this idea is nothing new. For centuries, people have tried to connect the dots, linking celestial events to things like the enormous Kamchatka earthquake back in 1952. And hey, to be fair, the pull from the sun and the moon is incredibly powerful. It literally creates our ocean tides every single day. The forces are real, no doubt. But are they the culprit for earthquakes? Well, the science on this is pretty clear. When we look at the Earth's own gravitational field, its true gravitational landscape, it has these little peaks and valleys because of how mass is spread out. But these variations are tiny, and they're incredibly stable over millions of years.
They're just way too weak to trigger a quake. The real story, the one that actually shapes seismic hazards, is all about the dynamic, restless movement of the Earth's crust. And that brings us to the true engine of earthquakes. It's not some mysterious force from above, but a relentless, powerful process happening right under our feet.
Think of our planet's surface as a giant jigsaw puzzle made of massive tectonic plates. And they are always moving, always grinding against each other in super slow motion. You can see it on this map, the Ring of Fire and other active zones. This is where almost all major earthquakes happen. These boundaries are where colossal amounts of energy get stored up, and an earthquake is what we feel when that energy is suddenly released. Now, there's one particular type of boundary that's responsible for the absolute biggest earthquakes on the planet, a subduction zone. This is where a dense, heavy oceanic plate dives or subducts right underneath a lighter continental plate. The friction here is just immense, and it creates the perfect conditions for these monster megathrust earthquakes. So check out this diagram. It shows what we call a locked zone. See, the boundary between the plates isn't smooth at all. Friction causes them to get stuck or locked together, sometimes for hundreds of years. But all the while, the plate underneath keeps pushing. This builds up a truly incredible amount of elastic strain. The best way to think about it is like a giant spring being compressed more and more and more.
For the longest time, this building stress was totally invisible. But with today's technology, we can actually watch it happen in slow motion. This is how we now measure the strain before the inevitable snap.
So, and this is the crucial part, we don't have to guess anymore where the stress is building. By using these networks of super precise GPS stations, scientists can measure the slow warp and bend of the Earth's crust down to the millimeter. This data lets us model exactly which parts of a fault are locked up tight and storing the energy for a future earthquake.
But it gets even more detailed than that. See, a fault isn't just one big locked section. It's more like a collection of really sticky patches. And that leads us to the anatomy of the rupture itself.
And these sticky patches have a technical name, asperities. You can think of them as the extra strong, superglued spots on the fault. These asperities are where stress really concentrates and builds up. They are the true hotspots, the points where a rupture is most likely to happen.
So here's how it plays out. When an earthquake starts, the rupture isn't random. It often kicks off near one of these asperities. And as the rupture spreads, it finally breaks through that stuck patch and bam! That's when the majority of the seismic energy gets released. That's the shaking we feel.
Okay, now get this, because this is a really fascinating, kind of mind-bending discovery. When scientists looked closely at big earthquakes, like the Kronotsky quake in 1997, they found something wild. The major foreshocks and aftershocks, they don't happen where the main break occurred. Instead, they cluster around the edges of the asperities. The part that completely ruptured actually goes seismically quiet. It tells us this is an incredibly complex transfer of stress, not just one simple release.
And this wasn't just a fluke, a one-time thing. This complex dance of shocks happening around the stuck patches turns out to be a fundamental part of how these big earthquakes work.
Which brings us right back to where we started, to Mexico, a place where understanding this science isn't just academic, it's a matter of life and death. So let's apply all these concepts to one of the most seismically dangerous regions on Earth.
The huge seismic risk in Mexico City is almost entirely controlled by the subduction of the Cocos Plate diving under the North American Plate. This is the exact plate boundary that unleashed that catastrophic Michoacan earthquake back in 1985.
A magnitude 8.0, an earthquake that literally reshaped the city and completely changed the field of seismology forever.
And here's the key takeaway. That 1985 earthquake became a perfect, though tragic, real-world test of the asperity model. When scientists analyzed the data, they found its aftershocks weren't in the middle of the break. No, they were clustered right at the boundaries of the main slip zones, right on the edges of those asperities. This was powerful confirmation that this complex rupture process is the key to understanding the risk right there in that region.
So what's the bottom line here? How does understanding all this stuff, asperities, tectonic strain, change how we look at the threat of earthquakes? Well, it means we can completely redefine that gravitational landscape we started with. It has nothing to do with a mysterious force from space. The real gravitational landscape, the real map of seismic risk, is a map of the accumulated tectonic strain right here on Earth. We're looking at the strain building along the US West Coast here, but the principle is exactly the same for Mexico, for Japan, for every active plate boundary.
And that brings us completely full circle. For thousands of years, we've looked to the stars for answers about the powerful forces that shape our world. But today, we have the tools to listen to the Earth itself. The story of our seismic risk isn't written in the cosmos. It's written in the slow, silent, but measurable buildup of strain within our planet's crust. By understanding these earthly mechanics, we can finally move away from the realm of myths and prediction and into the world of practical preparation. And that leaves us with the ultimate question, doesn't it? Now that we can actually map the stress building deep within the Earth, can we truly prepare ourselves for its inevitable release?
You know, for as long as we've looked up at the heavens, we've wondered how all of that up there affects us down here on Earth. It's this ancient, really captivating idea that the dance of the planets, the pull of the moon, might have some direct, powerful, maybe even dangerous influence on our world. Today we're going to dive deep into that exact mystery.
So let's just ask the question head on, right? Can all that cosmic alignment, that pull from the sun and the moon, could it actually trigger the next big earthquake? Is the next big one written in the stars? Well, that's exactly what we're here to find out, using geology and data as our guide. So let's get into it.
Okay, so look at this. On one side, you've got the elegant, kind of predictable clockwork of our solar system. That's an alignment that's actually coming up, by the way. And on the other side, the raw, chaotic, and unbelievably powerful reality of our planet's geology, the famous Ring of Fire. The big question is, are these two pictures connected?
To even begin to answer that, we first need to wrap our heads around one really important concept. See, when we talk about cosmic forces, it's so easy to just think of it as a simple pull. But the reality, well, it's a lot more interesting than that.
So, here's the crucial idea. It's not about the total gravitational pull that keeps Earth spinning in orbit. What really matters here is something called tidal force. And what that is the difference in the pull of gravity from one side of our planet to the other. It's a differential force that is constantly stretching and squeezing our entire world.
And this diagram shows exactly what's happening. A celestial body, let's say the moon, is pulling harder on the side of the Earth that's facing it, and it's pulling weaker on the far side. That difference creates these two bulges on opposite sides of the planet. So it's not just pulling Earth, it is literally deforming it, stretching it out like a piece of putty.
And get this stretching isn't just happening to the oceans. We are all living on what you could call a land tide. Every single day, the solid rock of the continents we're all standing on rises and falls by as much as 55 centimeters. That's about 22 inches. It's this huge planetary scale breadth that we never even feel.
So if our planet is constantly being stretched like this, who are the main culprits? Let's meet the primary architects that are responsible for this incredible daily deformation.
Okay, now this is where it gets really interesting. You'd probably think the sun, being so massive, would be the main player here. But it's this cosmic tug-of-war where proximity, how close you are, matters a whole lot more than just brute strength. The moon, because it's so close, has a much stronger tidal grip. It is the undisputed champion of our tides. The sun, for all its power, comes in at a distant second.
And this chart just lays it all out crystal clear. If we set the moon's tidal force as our baseline at 100%, the sun comes in at about 46%. So what about all the other planets in our solar system? Jupiter, Venus, all of them combined, their tidal effect, it's less than 1/10%. It is barely a whisper in this massive gravitational conversation.
But sometimes those main forces do align. On a day like this one, when the sun, the Earth, and the moon all line up, their tidal forces combine. And this creates what's known as a spring tide, which is a moment of maximum gravitational stress stretching our planet to its absolute peak. You look at that and you can't help but think, that has to do something, right?
It is a really compelling cosmic story. But just as we're looking up at the sky, the real answer requires a huge shift in focus, down to the ground, right beneath our feet.
Because as powerful as the cosmos is, the real story of why our planet shakes, it isn't written in the stars. It's a story of incredible pressure, friction, and time, unfolding deep, deep within the Earth's crust.
So here is what is actually happening deep underground. This is a subduction zone, a place where these massive tectonic plates are colliding. Now, for centuries, they don't just slide smoothly past each other. Instead, friction locks them together. But the plates keep pushing relentlessly, building up strain. It's like coiling a giant spring, tighter and tighter and tighter over hundreds and hundreds of years.
And these faults, they aren't uniformly stuck. You can think of them as having aspericities. These are basically extra grippy, high-friction patches that just refuse to budge. These are the specific spots where that tectonic stress builds to incredible levels.
They're the pressure points just waiting to snap and trigger a major earthquake.
And what's really fascinating is what we learned from earthquakes like this one in Kronotsky back in '97. After the main shock, the part of the fault that slipped the most, it went completely quiet. The aftershocks didn't happen there. No, instead they lit up around the edges, in the spots that only partially broke. And that tells us something huge. An earthquake isn't just one event. It's a complex chain reaction, transferring stress from one point to the next.
Okay, so we have these two massive forces at play, right? We've got the rhythmic pull from the cosmos and this slow grinding pressure from within our own planet. It's time to bring them together and deliver the verdict.
First things first, let's be absolutely clear. The stresses from these cosmic alignments are real. They are not pseudoscience. This graph shows the tidal stress on the Earth's crust, and you can see it peaking in early January 2026. This is a measurable physical force, no question about it.
But, and this right here is the absolute key to everything, it's all about scale. When you actually compare the size of that tidal stress to the tectonic stress that's already built up in a locked fault, well, it's not even a contest. The tectonic stress is thousands of times greater.
So here it is, the scientific verdict. Tidal forces simply do not have the power to cause a major earthquake. They can't load the gun. However, if a fault is already critically stressed, if that tectonic spring is wound to its absolute breaking point, it is plausible that the tiny additional stress from a tide could be that final straw, the feather that breaks the camel's back.
And this really just illustrates the whole takeaway. While humanity has always looked to the heavens for answers, the real story of seismic risk isn't found in cosmic cycles or planetary alignments. It's found right here, in the slow, relentless, and most importantly, measurable buildup of strain within our own planet's crust.
This really shifts our whole perspective. Knowing that the danger comes from measurable geological processes, not from unpredictable cosmic whims, it actually gives us power. So the final question isn't when will the planets align, but rather, how can we use our knowledge of the Earth itself to better prepare for what we know is eventually coming?
Cool part. How do we get from these positions to actual forces? Because remember, these aren't just dots on a chart. Each coordinate represents a massive object. And wherever there's mass, there's gravity reaching out across the solar system.
Exactly. You've got this constant pulling and tugging from the sun, the moon, Jupiter, you name it. And all of that together creates this invisible, totally dynamic landscape of gravitational forces all around our planet. It's like this incredibly complex web of poles that is changing all the time. So this whole landscape is invisible, right? We can't just look up and see it. Or can we? See, this is the real beauty of data. It lets us see things that are normally completely hidden from our eyes. So what if we could actually translate this gravitational landscape into a picture? So how do we actually do that? How do we bridge the gap between a table of coordinates and a visual representation of a force? Well, the answer lies in creating a powerful kind of visualization. You can think of it almost like a gravitational weather map for planet Earth. Okay, enough theory, let's put this into practice. We're going to use that ephemeris data to watch how this gravitational heat map evolves day by day during that one specific week in late December of 2025. Let's see it in action. And check this out, this just brilliantly shows how dynamic this whole thing is. On December 22nd, the moon's right there, creating these distinct red hotspots of high gravity. Then, fast forward to Christmas Day, the 25th. The moon's moved in its orbit, and you can see how those hotspots have shifted right along with it. By the 28th, it's moved even farther, dragging that whole gravitational landscape with it. It is literally a constant rhythmic sweep across the globe. So, we've successfully mapped this shifting landscape of gravity. But this isn't just a cool visualization. It has a very real, very powerful effect right here at home, especially when it comes to our planet's huge oceans. Okay, so who's really in charge of our tides? The sun or the moon? Your first guess might be the sun. It's unimaginably massive. But it's also incredibly far away. The moon, on the other hand, is our cosmic next-door neighbor. And because it's so close, it exerts a much stronger differential pull on us. It's that stretching force again. It pulls harder on the side of Earth facing it than on the far side. And that difference is the secret sauce that creates our tides. The mechanism is beautifully simple. Those red zones we saw on the heat map literally pull the ocean water towards them. This creates a bulge of water on the side facing the moon. But here's the wild part. It also creates another bulge on the complete opposite side of the planet.
So now you've got these two bulges, and our planet just spins on its axis, rotating us right through both of them, day in and day out. And that rotation through two bulges is why most coastal areas on the planet get 2 high tides and 2 low tides every single day. It's the rhythm of our planet, set by these invisible zones of gravitational force that we just made visible. So we've seen how a bunch of precise data can pull back the curtain on the invisible cosmic dance that governs our oceans. It really makes you wonder, doesn't it? What other hidden patterns and invisible forces are shaping our world all around us, just waiting for the right data to finally be seen? You know, right now, at this very second, our planet is being pulled in a dozen different directions by forces we can't even see. It's this constant cosmic dance, and Earth is right in the middle of it all. So let's dive into this incredible gravitational landscape and see how the pull of the cosmos literally shapes our world. What you're seeing here is basically that dance in action. Our solar system is just this dynamic web of gravitational pulls. I mean, everything from the massive Sun and Jupiter to the smaller tug of Mars is in a constant tug of war. And that heat map on the right, that shows how those forces create areas of high and low intensity right here on Earth's surface. It's this incredibly complex interplay, with every single body pulling on every other. So that raises a big question, right? How in the world do we go from this beautiful, almost abstract idea to the super precise measurements we need? You know, the kind of data that lets us send a probe to another planet or makes your phone's GPS actually. To really understand the tapestry, we have to start by looking at the threads that make up its foundation. Think of these as the warp threads, you know, the fixed, underlying structure that gives the whole pattern its fundamental shape. So what is this warp? Well, the main artist here is actually Earth itself. The warp is our planet's own built-in gravity, the pull that's generated by its own mass. But here's the thing, because that mass isn't perfectly spread out, the gravity isn't either. And this creates the permanent baseline gravitational field of our world. You know, if Earth were a perfect, smooth sphere, gravity would be exactly the same everywhere. But our planet is anything but uniform. The immense mass of the Himalayas, for instance, creates a gravitational high point, while deep ocean trenches create lows. This is what gives us that lumpy, static field. These are the warp threads of our tapestry. Okay, so if Earth's own mass creates that static foundation, what's causing all those swirling, temporary patterns we saw in that first image? Well, that brings us to the second set of threads, the weft. These are the threads that are woven across the foundation, and they come to us from deep space. These weft threads, they're the tidal forces. It's this constant, gentle tugging from the moon, the sun, and believe it or not, even the other planets. Now, unlike the static warp of Earth's geology, these forces are always moving, always changing, driven by the orbits and alignments in our solar system. They are constantly reweaving the tapestry, moment by moment. It's a term we hear all the time, right? But what does it actually mean? It's not quite as simple as you might think. So here's the crucial idea. A tidal force isn't just a pull, it's a difference in pull across an object. Let's take the moon, for example. Its gravity pulls strongest on the side of the Earth that's facing it, a little less on Earth's center, and weakest of all on the far side. This difference in force literally creates a stretching effect on the whole planet. And that stretch is exactly why we get 2 high tides a day. It makes perfect sense when you see it this way. The water on the near side is pulled away from the Earth, creating one bulge. At the exact same time, the Earth itself is also being pulled away from the water on the far side, which leaves a second bulge behind. It's an incredible planetary scale stretch. So who are the biggest players in this cosmic tug-of-war? Well, this chart makes it pretty clear. The moon is the undisputed champion, and that's purely because it's so close to us. The sun, even though it's absolutely massive, is so far away its tidal effect is less than half of our moon's. And the other planets, yeah, their contributions are measurable, but they're tiny in comparison. Okay, so we have our 2 components, right? We've got the static, lumpy warp from Earth's own geology, and we've got the dynamic, stretching weft coming from the cosmos. Now let's see what happens when we put them together. The total tidal force, that weft we've been talking about, is really the sum of all these different pulls. On any given day, the moon's double bulge effect combines with the sun's effect, plus all those tiny little tugs from every other planet to create one super complex tidal landscape. And that brings us to our specific case study.
We are going to freeze time right on a single day, just to see how these forces all came together to create a completely unique, and here it is. When we overlay the dynamic tidal forces of that day, the weft, onto the permanent gravitational field of the Earth, the warp, we get the final tapestry. This is it, the complete, true picture of gravity on January 4th, 2026. A fleeting and totally unique pattern. This global view is just stunning, but what does it actually mean on a more regional scale? Let's zoom in a bit and see how these forces play out closer to home. Looking at these three views, you can clearly see the large-scale patterns. The red areas show the combined effect of high-mass continents and the peaks of the tidal bulges, while the blue shows the opposite. The pattern is truly global, affecting every single point on the planet just a little bit differently. And here you can really see both the warp and weft at work. That deep red running down the spine of the country, that's the Rocky Mountains. That's the permanent warp. But notice that broader gradient fading across the continent, slightly stronger on the east coast and weaker on the west. That's the weft. That's the continent-wide tidal stretch from the sun and moon. Now, this is really cool. If we digitally remove the effect of the land masses and look only at the tidal forces, we can see exactly why this is happening. On this day, the cosmic pole creates a distinct differential, a different gradient across the continent. This is the engine of our ocean tides, pulling on the Atlantic and Pacific waters in different ways. And here's a fact that might just blow your mind. This force doesn't just pull on water. It is so powerful that it physically deforms the planet's solid crust. The ground beneath your feet is rising and falling by as much as half a meter, or almost 2 feet, every single day. It's called a land tide. The entire planet is literally breathing. So, I think the most important thing to take away from all of this is that the portrait of gravity we've been looking at isn't permanent, not even close. It is in constant, beautiful flux. The map for January 4th, 2026 is just a single frame in an eternal movie. As the Earth spins and the planets continue their silent orbits, the weft threads are constantly being pulled in new directions, creating a new tapestry second by second, day by day. Honestly, it's less like a map and more like a weather system. You know, seeing our planet's gravity this way really changes your perspective. It shows us that Earth isn't some isolated sphere, but an active, breathing body, intimately connected to and shaped by the gravitational currents of the entire solar system. It's a constant, silent dance between the ground right beneath our feet and the stars way up above. And as the celestial clockwork turns, this portrait is always being repainted, reminding us that even the most fundamental force we know is in constant, beautiful motion. So if this is what gravity looks like today, what will it look like tomorrow? You know, we all know what the Earth looks like, right? That big blue marble hanging in space. But what if you could actually see the gravity? I'm not talking about the planet itself, but this invisible landscape of forces that's constantly pulling and stretching it. Well, that's exactly what we're diving into today, the gravitational weather of our world. Okay, so check this out. This isn't some weather map you'd see on the news. No temperature, no ocean currents. What you're looking at is a snapshot, a single moment in time of the total gravitational stress on our entire planet. It's beautiful, right? But also kind of mind-bending. So how in the world do you even make a map like this? And what is it really showing us? Well, we're gonna break it all down. All right, here's how we're gonna tackle this. First, we'll look at our cosmic dance and the real center of the solar system. Then we'll meet the main players, the sun and moon, and see how the other planets get involved. After that, we'll figure out how to map all this gravitational weather. And finally, we'll put it all together to understand that amazing image for January 5th, 2026. Okay, first things first, we've got to bust a myth that almost all of us learned in school. You know, the idea that all the planets just neatly orbit the sun, like it's some fixed anchor in space. The reality, well, it's a whole lot more dynamic. And get this, look closely at the sun. It's not sitting still, is it? It's actually doing this little wobble through space. And that's because our entire solar system is basically one big interconnected gravitational field. Everything, all the planets, and yep, even the sun itself. So, now that we have that cosmic picture straight, let's zoom right back in on Earth. Who are the heavy hitters? What are the biggest forces shaping our gravitational neighborhood? Okay, so yeah, every planet plays a part, but let's be real. Two bodies just completely steal the show, the sun and the moon.
The sun is just so massive, its gravitational pull is immense. But the moon, even though it's tiny by comparison, is so incredibly close that its gravity has this huge, outsized effect. These two, together, are the main drivers of what we call tidal forces. And this is maybe the most important takeaway. Tidal forces aren't just about getting pulled by gravity, it's about getting stretched. It's all about the difference in that gravitational pull from one side of the Earth to the other. That's the key. And this visual shows that stretching effect perfectly. The side of the Earth that's closer to the moon gets pulled the hardest, right? So that creates a bulge. But here's the cool part. The center of the Earth is also getting pulled more strongly than the far side, so the water on the far side kind of gets left behind, creating a second bulge over there. And that gives us this fundamental two-bulge pattern that affects everything: our oceans, our atmosphere, even the solid rock beneath our feet. But of course, the sun and moon aren't the only ones in the game. All the other planets in our solar system, they add a whole other layer of complexity to the mix. Think of them as the gravitational modifiers. Now, their individual pulls are way weaker for sure, but when you add them all up, the massive tug from Jupiter, the closer pull from Venus, their combined force creates these subtle but totally measurable stress fields. They're basically tugging on our planet from all these different angles. And that's what starts to distort that simple two-bulge pattern we just talked about. Okay, so we've got these huge forces from the sun and moon, plus all these complex, subtle influences from the other planets. How on Earth do we visualize all of that at once? Well, we use an idea that's actually pretty familiar to all of us. We create a gravitational weather map. And it's a really great analogy, right? Instead of showing high and low pressure in the atmosphere that causes wind, this map shows us areas of high and low tidal stress, the spots where our planet is getting stretched and compressed the most. And reading the map is super simple. Just like on a weather report, the warm colors, the reds and oranges, are your high pressure zones. That's where the gravitational stress is at its max. And the cool blues, those are the low pressure areas, where things are a lot calmer. So with this key in our pocket, we're ready to unlock the story of our big day. All right, the moment of truth. We have all the pieces of the puzzle. Let's go back to that very first image and break it down, layer by layer, and really see the story of the forces shaping our world on that one specific day. So the first thing that just jumps out at you is this intense red zone, right? That is the primary tidal bulge. It's the spot on Earth getting pulled most directly towards the combined gravity of the sun and the moon. This is ground zero for tidal stress. Okay, now let's spin the globe around to the exact opposite side, and there it is, its twin. This is the antipodal bulge, and it's a perfect example of that differential gravity we talked about. The whole planet is literally being stretched along this line, creating these two major high-stress zones on opposite sides of the Earth at the very same time. But here's where it gets really fascinating. When you look at the Earth from the pole, you can see the pattern isn't perfect. It's not symmetrical. See all those complex swirls and arcs of stress? That is the signature of the other planets. All their combined off-axis poles are twisting and distorting that simple two-bulge pattern, creating this incredibly beautiful and complex field. So this naturally leads to a really interesting question. We've just mapped this whole intricate landscape for a single moment. Is this just what Earth's gravity field looks like all the time? Oh, absolutely not. And honestly, that might be the most amazing part of this whole thing. The map we've been staring at is just a single frame from a movie that never ends. As the Earth spins and all the planets keep moving in their orbits, this entire pattern of gravitational weather is constantly flowing and shifting across the globe, changing every single second. And that's really what it all comes down to. We live inside this incredibly dynamic, interconnected system. At any single moment, the state of our planet is a direct result of its exact position in this huge, invisible landscape of forces. A landscape that's been shaping our world since the very beginning. So the next time you look up at the sun or the moon or the night sky, just remember, you're part of this incredible cosmic dance. Every single day, like this one on January 5th, 2026, is just one unique moment in a vast, flowing cosmic river of forces. And that right there, that's the big question that drives us, whether we're living in the 18th century or right here today. We're going to look at three completely different lenses humanity has used to try and make sense of all this chaos. The scientific, the historical, and one that, well, it looks for patterns in the cosmos itself. All right, let's jump right into our first lens, the modern, data-driven, scientific approach. And to do this, we're going to look at a massive earthquake that happened off the coast of Russia to see exactly how scientists break down the incredibly complex mechanics of our planet.
So this huge event, deep in a really remote part of the ocean, it turned out to be the perfect natural laboratory. Scientists got to work right away, using these super sophisticated techniques that listen to the earthquake's sound waves. You can almost think of it like a planetary ultrasound, creating this detailed forensic analysis of what went down, miles beneath the ocean floor. Now, here's a really interesting and crucial concept: asperities. The easiest way to think of them is like rough, sticky patches on a fault line. So while other parts of the fault might be slowly creeping along, these asperities, they get locked up tight. And for decades, sometimes even centuries, they just sit there, building up and storing an absolutely immense amount of energy.
And what this science gives us is this beautiful, clear story of the quake. See, it wasn't just one single instant snap. Nope. This illustration shows the sequence perfectly. For decades, stress was building up. Then, smaller foreshocks started happening, like little warning signs. And then, boom, the main rupture began, starting a chain reaction that basically unzipped the fault line.
So the real kicker is right here in the data. Look at this. The main asperity, the one that slipped a staggering 240 centimeters, that's almost 8 feet. It had very few aftershocks. And you have to ask why? Well, it's because all that stored up stress was gone. The energy was spent. The aftershocks happened around the other patches, the ones that only broke partially.
Okay, so with this incredible level of understanding, you'd think we could pinpoint exactly when the next big one will hit, right? Well, this is where things get a little tricky. It really becomes a game of probabilities, not of certainties.
And to see this uncertainty in action, just look at these models for the Parkfield segment of the San Andreas Fault. It's one of the most studied fault lines in the entire world. And even there, depending on which model you look at, the annual probability ranges from around 4% to 8%. The models give us a crucial window for sure, but the exact timing, that's still deeply uncertain.
Okay, so now let's rewind the clock, way back. Before we had seismometers and these complex computer models, our only data was, well, the raw human experience. And this was captured brilliantly by writers like Daniel Defoe, who pretty much became one of the world's first modern journalists.
After that devastating 1703 storm, which had full-on hurricane force winds, this is how Defoe described London. The roofs were torn off, buildings looked like skeletons. It's such a stark, visceral contrast to the clinical data from the scientific paper, isn't it? This is the data of human feeling.
I mean, the scale of this tragedy was just immense. An estimated 8,000 people died, a huge number back then. But instead of just chalking it up to an act of God and moving on, Defoe did something radical. He put out ads in papers asking for eyewitness accounts from all over the country. He collected them, compiled them, and created this incredible document of the storm's human toll.
And he documented the timeline just meticulously. He tracked the storm from the first terrible gusts to the catastrophic peak in the dead of night, and then the devastating flood that followed when the wind shoved a massive storm surge inland. In its own way, this is data. This is history as data.
But what if the patterns we're looking for aren't just in the earth beneath our feet, or in the stories we tell? For thousands of years, some have looked even further for answers, out beyond our planet entirely. This search for larger cosmic patterns is our third and final lens. Okay, so now we're going to explore a very different kind of perspective from one of our sources. This one suggests a potential link between planetary alignments and periods of major change here on Earth, both geologically and historically. The specific focus is on the conjunction of Saturn and Neptune, an alignment that happens roughly every 36 years. The source material points to what it describes as these really notable clusters of events. For instance, a massive magnitude 9.0 earthquake back in Kamchatka in 1952 occurred during that cycle's conjunction. And the source notes a similar timing for the eruption of Krakatoa, the huge new measured earthquakes in the US, and even the deadliest earthquake in all of recorded history. So here's where it gets really interesting: the radical difference in explanation. You know, science points to measurable physical forces. Tectonic plates grinding against each other, clusters of events are seen as a product of randomness, or maybe regional stress. This other source points to a symbolic cyclical pattern, suggesting these alignments act as markers for periods of instability, where the structure of the planet, symbolized by Saturn, is dissolved by the influence of Neptune. So, okay, we've got these different lenses, scientific, historical, cosmic, but why does any of this really matter? Well, because understanding, especially scientific understanding, is the bridge. It's the bridge that takes us directly from theory to actually saving lives. Remember that incredibly detailed scientific model of the Kamchatka earthquake we talked about? Well, that kind of meticulous study has been absolutely instrumental. It's what has fueled the development of the sophisticated warning systems that can protect coastal communities from one of nature's most destructive forces, tsunamis. And this is how it all works today. Seismic sensors pick up the quake, buoys out in the deep ocean measure the wave. That data gets beamed via satellite in real time to warning centers, who then issue the alerts and people get to safety. And you know what? This brilliant system was actually activated after that very 1997 Kamchatka quake we discussed. The warnings went out, evacuations happened, and the tsunami had minimal impact. It's a perfect example of science in action. So in the end, each of these lenses gives us a really valuable piece of the puzzle. The scientific lens, it gives us the hard data we need to build and prepare. The historical lens gives us the human context, reminding us of the real, tangible impact. As we face the future on this incredibly dynamic planet of ours, the real challenge is to combine that data and that context to cultivate the wisdom we're going to need to survive. Does precision matter in our daily lives? Well, as it turns out, these tiny-looking shifts in the cosmos have a huge impact right here on Earth. Just think about the tides, for example. The gravitational pull of the moon and the sun is so powerful that it actually causes the Earth's oceans to bulge out, creating the high and low tides we see every single day. This heat map really shows those forces in action, literally pulling and stretching our world. It is, without a doubt, the most visible daily reminder of that cosmic tug of war we find ourselves in. But it doesn't stop with the tides, not even close. The GPS in your phone, navigating missions to Mars, predicting where asteroids might go, and even understanding long-term climate patterns, all of it depends on this incredible precision. It really is the invisible foundation of our modern world. So when we take a step back and we look at the big picture, what does all of this data really tell us about our place in the universe? It tells us that we're not just living on a planet. We are passengers on a cosmic vessel. We are hurtling through space at thousands of miles an hour, intricately connected to everything else in our solar system, guided by these silent, powerful. So the next time you look up at the night sky, just remember those invisible forces at play. Remember the silent gravitational dance that governs our entire world. And maybe ask yourself, how does it feel to be a part of something so vast, so intricate, and so perfectly balanced?